Our first speaker is Prof.Dr. Mohamed Mokhtar Mostafa, Professor of Physical Chemistry at the National Research Center, Cairo, Egypt, and Faculty of Science, King Abdulaziz University, Jeddah, Saudi Arabia. Obtained his PhD from the Faculty of Science, Cairo University in 1997. From July 2012 till now, he occupies the position of Professor of Physical Chemistry at the National Research Center and King Abdulaziz University. Professor Mokhtar research interest is in materials chemistry, in the application and properties of nanomaterials, heterogeneous catalysis, and catalytic materials. He contributed and participated in a number of international and national collaborative scientific projects. He has published over 104 refereed publications and 8 international patents, and he has worked on numerous projects with public and private sector organizations.
Okay.
Proceed, Dr. Mokhtar.
So, thank you very much for your nice introduction and for
it is a very short
just
introduction.
Please switch off your. So, thank you very much. Thank you very much again for the kind invitation to attend this great ceremony here at Cairo University, our university where I have started the PhD studies here. So thank you very much again, and I would like to introduce my talk today. We're revolving around something important to the industry. It's a project funded by a great company, which is SABIC from Saudi Arabia. And this project is non-conventional oxidative dehydrogenation of propane to propene over vanadium zirconia catalysts. This is part from the current project, which is funded by 1.2 million, and is going to be extended for next years according to the proof the concept inside this presentation. So first of all, this project, as I said, has been initiated to support SABIC internal research activity towards the technology, which is the development of the olefin business in purpose production for the propylene. And second thing is SABIC itself having an action for the citizenship to support the local Saudi universities to grow in the research. It's also selected the search that related to the applications in the company itself. So project was tailored towards propylene in purpose technology. So what's the difference between propylene in purpose technology and propylene production from propane? That will explain during the next presentations. So we'll focus on short alkane dehydrogenation by chemical looping, which is new novel method for the production of the propylene in purpose. And we have to prove the concept in order to have financial support, in order to convince the industry to continue support such a kind of work. And it includes, of course, some catalyst development and some inventions. First of all, we have to know the main business driving force for a company to support such kind of work. If you look about the petrochemical productions worldwide, 48% from these productions are mainly for the ethylene and the propylene, where propylene considered to be 20% out of the whole production of the petrochemicals in the industry. And of course, we know the applications of the propylene as a starting material, as a monomer for the production of the great polymer polypropylene with many wide applications in our daily life. So the world demand of the chemicals around 575 million megatons per year, in which ethylene and propylene account for 48% of the total chemicals. This is why there is main business driving force towards such kind of projects. Then, propylene in general produced as a byproduct from steam refining steam cracking, fluid catalytic cracking, FCC refineries. With the demand of growth of the exceeding this production, people now thinking for having another way of the production of propylene directly. So it's called propylene in purpose, not as a side product from refineries or FCC. So if you look at the figure here, you can find the blue columns related to the steam crackers, production of the propylene, and the gray one for the refineries, but in purpose was very low in 2011, but it's going to expected market in 2026 to be much higher than the original starting one. So again, the forecast for propylene in purpose is a target of many companies, and for that reason, SABIC could think for start now, not before, not after, and they will lose the market if they not start the challenge. Usually, propylene could be produced either by propane dehydrogenation, so we can do directly dehydrogenation of the propane, but this process is endothermic process, high temperature produced during the reaction, so thermodynamically limited because of the high temperature will cause deactivation of the catalyst, which is mainly consists of platinum metal supported with other supports, and that causes increase of the crystal lattice of the material, grain growth of the material, and this causes poisoning to the catalyst itself. So it's unfavorable method to direct dehydrogenation of the propane to the propylene. Second idea, which is mostly of the literature of the people working on, is the oxidative dehydrogenation. And oxidative dehydrogenation, instead of using direct dehydrogenation of the hydrogen, you are passing oxygen, either hard oxygen or soft oxygen in the form of an oxidizing agent like NOx, CO, COX, any source of oxygen. And this oxygen should take the two hydrogen atoms and then produce the propylene directly. The advantage of this method is it's exothermic process, so you don't need to have high temperature, but the problem is lower the thermodynamic limitations, but the problem is the production of the presence of oxygen in the stream after doing the first process by, it will burn the product, so it will affect the yield of the propane. Instead of have propylene, you will have loss in the yield of the propylene due to burning of the propylene that produced by oxidative dehydrogenation using the oxygen in stream. So you are losing the yield, although you could have a good selectivity towards this process. So again, we have also in industry there are separation problems. To separate the carbon dioxide that produce or carbon monoxide, cryogenic problem for the exothermic process. So you have to make cooling, and such also causes cost. And the cost in industry is unfavorable. So how can we think as a scientist to solve the problem? This is the question. If the direct dehydrogenation is a problem, and if I pass oxygen directly is another problem. So the idea came early even before this project. I thought, why not use oxygen the lattice? Why not use oxygen of the catalyst itself to be labile? Comes out, takes hydrogen, return back, and finished. You don't have oxygen, you don't have hard oxygen, you don't have even soft oxygen. So this is the idea which is called non-conventional oxidative dehydrogenation via what's called a chemical looping process. So the first process is this is a metal catalyst. It's used as a reducer, so it will take the two hydrogen atoms from the surface of the propane to propylene, and then you have to return the oxygen lattice again to the surface of the catalyst by passing air and heat, so you can add oxygen to the lattice. But this idea needs two types of thinking. We have to think for which material could offer this labile oxygen. What's the active centers? It's only oxygen, or we need other active component to help to avoid what's expected as a coke formation during the process. So this is called a catalyst design problem. Second one is the system itself. Which kind of system could help you to test your reaction? Is it only fixed bed catalytic reactor or what? So again, this is the idea. Propane should pass over the surface of the catalyst, taking oxygen, and remove the hydrogen, then propylene is coming. But I have to return the oxygen again to the lattice after removing these two oxygen atoms from here. So the goal, as I said, we have to think for 2 points: catalyst design itself and catalytic system. For the catalyst design, usually the catalytic people should think for first, if there is a support, what kind of support you have to select is the support that have oxygen mobility as well as a good interaction with the active species on the surface. Good interactions for the catalytic materials is a good dispersion of the active sites, or if it agglomerates the monomer on the surface of the catalyst. So catalyst design is a question, and you have to find an answer for this one. Second part in the design, as I mentioned, we need labile oxygens coming out and the capability of the material to retain the oxygen to the surfaces. So of course, not molecular oxygen, should be oxygen, free radical oxygen, oxygen -1, and so on. Yeah? So for the catalyst design, we'll go through the first journey, then I will take back again to the catalytic system. So I'm gonna to talk about the catalyst design first. And for catalyst design, I said with Professor no, with you. with Professor Rifat.
ده انت كده هتزعلني منك بقى اقفل المقامه يا ابني.
So I said to Professor Rifat Hilal during his visit at King Abdulaziz University, thinking for giving him the idea. I said to him, I need some computational chemist. I need one of the chemists in the computational urgently. And he helped me, although it's very difficult to take this guy and work with us. So the first question was, what I suggested according to our experience for the supports is the zirconia as a support. But what my question was, which phase of zirconia could be suitable for the oxygen labile in its crystalline structure? So we have 3 different phases: the monoclinic zirconia, tetragonal zirconia, and the cubic zirconia. And of course, we're dealing about the surface of the material, not the bulk of the material itself. So what our computational chemists done, they start to take every phase and remove 1 oxygen from the lattice and count the energy of how much energy is required to detach this oxygen from the surface of each phase. So we have to go here, we can compare the results. We could find the best value is 5.77 or 5.88. These are the easiest phases of zirconia that we have to use in order to remove the oxygen or have the ability to make what's called the labile oxygen inside the lattice. Of course, this computational work is parallel with our experimental part. It's not only computational, but from my experience, I know how much you can spend without computational chemistry. How much time, how long time you could spend. Trial and error. At the end of the story, you could stay with computational chemists, give him the idea, explain it quite well, and let us shorten the time for solving the problem. Second point is, if we add active species on the surface of this zirconia, which have been selected as the vanadium, which is the active species usually used for the oxidative dehydrogenation. So if we add 1 vanadium atom, this is the first one, and again add the second one, already we selected the best phase of zirconia, then add the second one and asking ourselves, Is vanadium will be dispersed as a monomer on the surface, or will be agglomerated as a polymer on the surface. And what we got as a result, they are tend to make polymer on the surface of the phase that have been selected by the zirconia. So we are expecting now, if we have a zirconia, we are using the cubic zirconia of lower energy for evacuation for the oxygen. Second part, what's the kind of vanadium will be dispersed? It will be polymeric vanadium on the surface of the zirconia. So going now to the preparation method, we used a preparation method, modified precipitation method. It's only precipitation with some, of course, tricky things during this precipitation in order to control the nucleation of the material, the nano size of the material, so it's not usual precipitation. Then hydrothermal post-treatment by hydrothermal treatment of the cake, of the material. Then we do filtration, washing, and calcination of the cake at 500 degrees centigrade according to the TGA data. Many catalysts have been prepared with different vanadium percent on the surface of the zirconia. I'm not going to discuss the series zirconia system in this lecture. So, first we have to do the physiochemical characterization, which is usual techniques. Usually you have to go to the surface area, X-ray measurements, SIM, Raman, TIM, and so on. But the most important thing here, okay, we need the characterization, usual characterization, physiochemical one. But the most important thing in our case is not the crystal structure or whatever. The most important thing is to study the reducing ability, the oxygen hydrogen cycle on the surface. And for that reason, we have to go to the hydrogen temperature programmed reduction method, oxygen temperature programmed reduction method, and then a cycle. Hydrogen temperature programmed, then oxygen temperature programmed. It means something like to pass the hydrogen first, reduce your catalyst, and show at what temperature you have the profile for this complete reduction. What happens if you add another vanadium? It could affect this reduction or not. Then pass oxygen, uptake the oxygen again to the surface to see if it's capable to uptake the oxygen again or not. So we need a cycle of reduction, oxidation of the material itself to design expected catalyst for the production of propylene in purpose. So this is a machine which is going, this is a machine from Quebec 3000. This is a normal machine coming by the company, Quantachrome company. But I will explain to you what happened to this machine later. But this is the first for TBR, TBO measurements. So this is a characterization. X-ray is telling us no change in the phase of the cubic of the zirconia. Cubic zirconia, whatever you add vanadium, 1, 3, 5, 7. There is no change. There is no other phase for the vanadium appeared, but spectroscopy techniques could show you the difference. Here is the zirconia, pure zirconia, but when we're adding vanadium here, we have the peaks. And this peak could be for the polymerized VOX, for the polymerized vanadium, high-ordered octahedral vanadium on the surface of the zirconia itself. Again, the Raman spectra confirmed these structures by having these phases that not appeared for the pure zirconia itself, and these speeches are related to the polycrystalline vanadium on the surface of the catalyst. Many characterizations are there, but the most important thing, as I told you, the hydrogen-oxygen cycle. Here the temperature programmed reduction is simply we adding the catalyst in the machine, passing the hydrogen, and then following up, increasing the temperature gradually to see what's going on. So we have here the low or the negative direction for the desorption of the absorbed material on the surface of the catalyst itself. Then here we have the peaks for the reduction. We could say here reduction of the surface of vanadium species, which is the easily reduced will come at lower temperature, and the difficult to be reduced should come at a higher temperature. So if it's on the surface, this could be easily reduced. If it's in the bulk or the bulk vanadium itself, it will be difficult to be reduced. But zirconia itself, here, which is, of course, it's very difficult to reduce zirconia as a material, but Bases of vanadium, there are some peaks as low temperature and high temperature reduction ability. Still, this recyclability under work till now for other catalysts, not only for these catalysts, but also for other catalysts for the cycle of hydrogen oxygen. So the catalyst design is finished now. We decided to synthesize vanadium supported zirconia catalyst to be the first series, the first batch of the catalysts that should be tested for this process. But the problem is, what the catalytic system is suitable for this reaction? First, the microcatalytic reactor, which is a fixed bed reactor, general fixed bed reactor, at the beginning said, okay, if you would like to test for the fixed bed catalytic reactor, I'm going to have 1.2 million from this project. It's quite enough for me because I have the fixed bed reactor. But as a scientist, I'm telling you from the beginning, fixed bed reactor will not solve the problem. So if you need to increase the fund up to 3 million, I'm going to use a fluid-based bed reactor, which is more suitable because in this process you have shaking the catalyst, you make the reduction, you have the catalyst inside, and you can do the process nicely. It's complicated technique, it's expensive one. What the industry had with me, they found it 1.2 and they bought the machine from outside. That's what happened in this one. But they bought it from Canada, trying to, but I'm going with another idea, but not I'm going to. That research direct us to think for new reactor. What's the new reactor and why? Let us discuss first the results. These are results using the fixed bed catalytic reactor. I mean this reactor, so look at this one. Here is the reactor inside this room. The reactor is inside, and we have to pass the gases from this gas flow here to refine the gases, and the gases coming, passing through the catalyst to go to the GC directly, so it's called in situ measurements for the production. So GC is working, FID, TCD, so it's time taking until you have separation of the products, and then you go to the computer in order to see the product of your reaction. This is the data coming from using fixed bed catalytic reactor, using our catalysts, vanadium zirconia 1, different catalysts with different loading, even zirconia without loading any catalyst. And this is carried out at 300 degrees centigrade, very low temperature. This very low temperature, we could not expect anything. The conversion is very low. This is a conversion percent. Yes, we have high selectivity towards the ethylene, which is not our target. We need the propylene. So at low temperature, low conversion, low selectivity towards propylene. When we increase the temperature using the same fixed bed catalytic reactor, honestly speaking, it's another fixed bed catalytic reactor. So I have two in my lab, one working at lower temperature, one working at higher temperature, but the two reactors are fixed bed catalytic reactor. At high temperature, we see for all the catalysts, even we have the highest conversion for the 7 vanadium zirconia 1 with a high selectivity towards propylene. So we have a nice design of the catalyst, but we don't have a good results using such a fixed bed reactor. What's missing? What's the problem? So we have to think, it takes time until you have the product passing through the GC, FID, TCD, separation, 20 minutes. In order to, 20 minutes you are passing only propane. What happened during these 20 minutes? On the surface of the catalyst, which is proposed to remove the oxygen, and you need later on to pass oxygen in. A lot of questions. So we studied the durability, I mean the lifetime for this catalyst. Using also the fixed bed. This is the first run. This is the second run after passing oxygen. We said, okay, for 30 minutes we could pass oxygen alone on the surface of the catalyst after the reaction, and then passing helium to return the oxygen to the surface, and then test the catalytic activity again. It's still active, but there is a deactivation of the catalyst after few minutes, after 1 hour, still to deactivate using this process, using first cycle of oxygen reoxidation of the catalyst, reoxidation of the catalyst again, testing the catalyst many times. Then we came to ask us, what we can do. Look at the system that what we are using for the TBR measurement. This machine, we only do a pulse to the propane, then passing this pulse, passing the hydrogen, it could reduce. What if I connected this machine directly to MS? So I convert the machine to the company itself. And instead of doing a new reactor, I have the machine, I could use it as a reactor, just connect it to MS, and look what's going on using transient pulse technique. So here, we went to this machine, which is commercially applied for another purpose, which is TBR, TBD, chemisorption measurements, and you connect our catalyst here. This is a reactor. Gas is coming through here. So instead of coming through here, I could control by the loop. So I have how many quantity of the gas I could pass through the reactor and then detect the product by MS and see what's going on using this machine. So here to explain what's going on, I will pass the propane controlling by the valve here. So control only 3M, it will have directly the signal for the propylene that produced after the oxidative dehydrogenation of the surface of the catalyst. Then I will flush the helium to clean the pipes completely. After passing helium, then repeat the reaction again without restoring oxygen, without reoxidation of the catalyst, in order to see how long time it works without repassing oxygen again to the surface of the catalyst. Repeating this many times. At the end of the story, I will make flushing and then pass oxygen, then make flushing, then do the reaction again and so on. This is the idea. It's only pulse, not look at this flow because I couldn't control. It's pulse by hand on this valve. Just open, close. You have only 3M selecting from the gases that are coming from outside. Pulse, pulse, pulse. Transient pulse technique, which is called chemical loop oxidative dehydrogenation reactor for the process. We have a lot of data, of course, we have to go through, which is peak is suitable. We have to compare because there are some contradictions from MS. MS itself is difficult to say this is to propane, this is to propylene is not enough data. So it takes time until we confirm which peaks related to which phase of the gases are coming from the reactor itself. But before doing the reaction, we have to test thermal cracking, only thermal cracking without catalyst. Just passing the gas on glass pads. Glass pads inside the reactor passing gases at different temperatures. At 400 degrees centigrade, there is no thermal cracking, but 500 degrees, 600, 700, there are thermal cracking without catalyst. The propane itself could be cracked, and the detected conversion is low, selectivity is high, but this is for the cracking. In order to avoid cracking from the catalyst efficiency, we have to select the 400 degrees centigrade as the temperature for testing the real catalytic activity of our catalyst. So we can avoid the thermal cracking. Only the conversion now will be related to the catalyst for testing the catalytic efficiency and selectivity. So we start to have the first preliminary results from the chemical loop. At 400 degrees centigrade, it's nice conversion. Above 65% conversion, with very high selectivity towards the propylene and low selectivity towards selenium. These results is good to prove the concept, but it's not good for the industry. Industry needs much more higher conversion, much more higher selectivity of your products and for that reason, they are happy by the machine, they are happy by the concept, they are agreeing that we prove the concept, but they will extend the project because we are preparing a very nice catalysts, working at very low temperature, and we are going to patent our work shortly, inshallah. And just one point, okay. 1 minute for the discussion. This is very important part. I have to tell. Because people start to interest in this work. Now it's published only in Science and published in Angular Chemie for such kind of work, some ideas by other people. What they mentioned, we had vanadium on the surface of aluminum as a support, and they said if you have the propane passing over the vanadium itself, it will be converted into V positive 3. V positive 3 is very active, highly reactive, and the higher the reactivity, the less the selectivity, you do the formation of the coke. So it favors the quick formation, and accordingly, this is why the catalyst could be decayed, and this could explain to us what happened for the fixed bed cathodic reactor when the catalyst decayed. Probably we have the same problem. What's the solution we have to find before the others? This is our suggestion. Our suggestion from also our work before, if we control the oxidation state of vanadium by adding OH group. If adding OH group, you have V positive form. So you're controlling here the acidity of the surface of the catalyst itself. Controlling acidity will decrease the reactivity of the vanadium, accordingly will decrease the cock formation of the surface and could resist the decay that could be faced later during this process as well. So at the end of my talk, I have to come to the conclusion, which is we developed catalysts for the oxidative dehydrogenation, non-conventional method for the propane into propylene. The ninth thing is a conversion of the reactor or the machine to another reactor in our lab, which is called chemical loop catalytic reactor. Transient pulse chemical loop reactor fabricated in our by our team in our university. And to prove the concept, to really prove this concept, we are waiting for, as I mentioned, 2 papers and 2 expected patents very near. I would like to thank my colleagues who already part of this work, the head of the division of the physical chemistry department, Professor Mostafa, Dr. Tarita from Saudi University is working with us in this project. Professor Narasima Harao from India is also one of the team work, me myself. And I would like to thank, of course, the people from SACIT. Our team, to be honest, we are working in 4 teams. Our team was the idea, with the machines, everything is coming, but we have another team working in parallel to us, is in SACIT. Another team working in United States of America, and another one in Cairo. But again, it's our idea, it's our invention, so everyone would be happy to fund and refund such kind of work. Thank you very much.
Thank you, Dr. Mokhtar. And any questions?
I have a few, not questions, number one, you have to be very rich to make all this. So I know Sabit and I know Aram. Yeah, that's very important. Number two, I would like to ask commercially, propane and propylene. What's the difference between the 2 commercially? Is propane has a higher value in the commerce than propylene, or both are equal, or propylene is more demanding?
As explained to you at the beginning, propylene is more demanded because of the propylene as a start, as a monomer, converted into polymer, into polypropylene with many applications. The issue is, propane is coming as a side product, but how to make value from the propane? To make value from the propane is to convert it, one of the issues is converted into propylene. But propane itself is useful as well.
Right.
Yeah, for that reason we are producing propylene in purpose, not as a side product, but also to convert the propane, which is coming as a side probably, with a lot of gases, with other things, to separate them and to convert them to most valuable material, which is propylene.
Okay, the second question is more scientific. It's you have the main problem that you have, I think, or that you have, is the cracking.
Yes?
Is the combination of cracking at temperature with the catalyst.
This is one of the problems. It's not a problem. It's the production of propylene itself could be coming from thermal cracking.
Yes.
Okay.
So
Thermal
both.
cracking to the propylene. We have both thermal cracking, but we have to select a new technology. This technology working at low temperature, using catalysts, which is environmentally benign catalyst, for example, not expensive one, for and it's a nice system like what I'm showing to you, which is could be scaled up later on for the industry. You will be happy. You avoid the exothermic problem, the endothermic problem, the cryogenic, the separation. This is the design.
Thank you very much.
Yeah.
Thank you. Any question, please? Any question?
Okay.
Okay. Thank you very much for coming.